And off we go. Okay, good deal. So, real quick before we get back into the math, don't forget about the attendance quiz. Probably about a minute and a half remaining, so make sure to get that done. Canvas app, submit the number for the quiz for today's date. Don't forget to confirm that you have the point recorded. Okay. And side note, I'm probably going to stop making these reminder announcements at the start of class. So, anyway, make sure you have a system in place to ensure that you will always do the attendance quiz. Okay. All right. So, last time we talked about how to visualize partial derivatives in the context of graphs. Again, you have to sort of partition in your mind the calculus of graphs as separate from the calculus of, for example, level sets. Totally different geometric interpretations of the exact same algebraic constructions. Okay. All right. So, so conveniently, very nice and familiar, a partial derivative in the context of graphs is the slope of the tangent line, just like in single variable calculus. Don't forget we have to emphasize this is just for the graph point of view. And don't forget we have to specify in which direction, and of course the direction is the direction of the variable that we're taking the partial with respect to. Couldn't be more expected, right? If you were going to guess, this is probably what you would have guessed. Okay. All right. So what about if we look at different pictures that we draw to represent multivariable functions? In this literal picture, keeping in mind that, I have a domain, we draw the domain. I have a target, we draw the target. The function takes points from the one to the other, we draw the action of taking a point from one to the other. In this kind of a picture, what's a partial derivative look like? First, for just rhetorical purposes, I'll point out it's definitely not a slope. Right? There's no tangent line to talk about, and so that point of view makes no sense here. All right. So let's think for a moment, what does it mean to take a partial derivative? And again, I'm going to take a partial with respect to y arbitrarily. That means we're going to hold x and z constant. They're not allowed to change. That means whatever these values are, for x and z, they're not allowed to change, which means I'm kind of confined to that line, something like this. And the question then becomes, all right, looking at the single variable function where I think of, for a given value of y, indicating where I am on this line, there's a corresponding output value of f, indicating where I am on this line. And how do we interpret this derivative? Well, we have an old point of view on derivatives, and that is that a derivative is a relationship between input change and output change. And so this is how you might, for example, view that. Input changes we represent by little displacements over here in the domain. Output changes we represent by displacements over here in the target. Of course, what displacement could we possibly be talking about in the domain? Well, we're not allowed to leave this gray line, right? We're confined to that gray line. X and z must stay constant. That's what a partial derivative says. So really, the interpretation is just kind of a callback to single variable calculus. That the partial derivative is a relationship. It's what you multiply by this change to get that change. Right? It's a little bit unsatisfying, arguably. Again, there's no slope, there's no picture, there's no shape to talk about. But that's how I see it anyway in this context. Okay. All right, moving along. What about on level sets? All right, now there's different ways to go about this. I'm going to tell you what I think makes the most sense to me anyway. So keeping in mind level sets, how do we understand level sets? Well, it is nice that they are lower dimensional than graphs. And for example, here I'm drawing presuming we have a function of two variables, and so I've drawn some level sets here in a two-dimensional xy plane. Whenever I'm looking at level sets in the xy plane, I think about topographical maps. I think it's the easiest thing, right? And so I just imagine that, okay, this is representing some sort of a hike that we're out on, and there's some sort of a hill, and each one of these lines represents a constant altitude. Now, it might not actually literally be that the function f is representing altitude, but I just like to think of it that way. Okay. So, reminder, in that point of view, height, altitude, right, is how you draw graphs, right? So weird little quirk, the altitude function is kind of a peculiar function in that the mountain you're talking about is the graph of that altitude function. Right? So a nice little observation. So we already know that level sets are cross sections of the graph. And so said differently, these level sets, if you're thinking about height, these level sets are cross sections of the hill whose climbing around on is being represented by your contour map. Right? So it's a lovely metaphor. Okay, so well, if we're climbing around on some mountain, and let's just play the scenario of suppose I'm going in the x direction. If I'm going in the x direction, let's just think about what that hike would be like. And I'm noticing that I cross the contour lines over pretty short horizontal distances here, right? Does not take much horizontal distance to gain whatever, let's say 100 feet of altitude that may be between these contour lines. If you're gaining altitude over short distances, that's steep, and that would mean that the slope is high, and that would mean that the partial derivative is large. Okay, now, same setup and everything, but now imagine we're going in the y direction. As you're going in the y direction, well, you're still crossing contour lines, but it takes a much greater amount of horizontal distance to actually cross those contour lines. Think about this being a hike. If you were going to gain the same 200 feet of altitude, but over this much distance horizontally, instead of this tiny, teeny distance horizontally, it doesn't seem like it'd be as steep. Right? Same amount of altitude gain over a much lower horizontal distance. And so I think that slope is less, and therefore that partial derivative would be less. So roughly speaking, the punchline then is whichever direction of partial derivative you're talking about, just look and see how close together the contour lines are in that direction. The closer they are together, the greater the absolute value, anyway, of your partial derivative. Everybody good? Okay. All right. Okay, moving along. Okay, so let's talk about linear approximations, a little bit of a change of gears. I'm sure y'all remember at least some of this from Calc 1, I suppose, right? A long time ago. But at least I hope y'all recognize this function. So this is called the linear approximation of a function. And by the way, real quick, I don't want to just assume that a linear approximation exists. There are plenty of functions that don't have linear approximations. Absolute value of x. The graph of absolute value of x does not have a tangent line. Doesn't make any sense. No such thing. Right? So what it comes down to is the function differentiable. So for the moment, I'm just going to say if it exists, under what circumstances does a linear approximation exist in a natural, meaningful way? Punt. We'll deal with that later. If it exists, this has to be it. Okay. And specifically, what that means to say that this is the linear approximation, what that means, this is the unique degree 1 polynomial that agrees with L in the value it takes at the point A, and it also agrees with F in derivative at the point A. So I like to think of a linear approximation as again, it's a degree 1 polynomial. Okay, but it's a function that's mimicking F in value, and it's mimicking F in derivative. It's a shameless ripoff of F. in terms of valuing derivative. Is everybody okay with that? It's not necessarily the same point of view you saw in your Calc 1 class, but this is a reasonable way to do it. All right. So, by the way, make sure you can prove this. In other words, make sure that you can take this formula and show that it satisfies these equations. As you do that, one thing to keep in mind is that that's a constant. This term here, this whole term is a constant. And here's the subtlety that a lot of people forget. This factor right here is a constant also. Kind of doesn't look like it. You see f prime and you think, ooh, that's a function. That's a derivative, so it's a function, and so maybe it's not a constant. But f prime is being evaluated at the point A. Once you plug in the point A, this is just a number. It doesn't depend on x. You've plugged in already for the x. Okay, so that's a constant as well. And obviously, of course, this A here is also a constant. So when you take the derivative, it falls out very quickly. So fill in those details, make sure you're good at that. Okay, so with that observed, let's try to figure out how we can extend this to a multivariable setting. And it's going to be kind of a copycat sort of a deal. Now notice that instead of a function of one variable, now we're talking about a function of several input variables. Right, multivariable function. I'm going to point out still real valued. We'll talk about vector valued in a bit. Right, so for the moment, still a real valued function. In other words, one output value only. All right, so a reasonable definition of a linear approximation would be a unique first, degree 1 polynomial that agrees in value with the original function at the point where you're doing the approximation, and also that agrees in first derivative. And the only thing is that there's several different first derivatives at this point. We got multiple input variables, and so therefore there's multiple different partial derivatives. And all this is saying right here is I want L and F to have the same partial with respect to x1. I want L and F to have the same partial with respect to x2, etc., etc. Last statement, I want L and F to have the same partial derivative with respect to xn. Cool. So it's really kind of a copycat definition, and I hope it wouldn't be too shocking if I were to suggest that this is the formula that does it. Now that needs to be checked. So I think this is a nice exercise. And let me remind you, just like up here, that's a constant, and that's a constant, and that's a constant. Well, likewise here, that's a constant, that's a constant, that's a constant, et cetera, et cetera. That's a constant, that's a constant. So there's just constants all over the place in this formula, right? So again, pretty easy to take a derivative of it. And whatever you want to take the partial derivative of L with respect to, just make sure you get what you're supposed to get. Everybody see the suggestion there? Just, directly confirm, if you would, that property 2 holds for this function. Okay. All right, healthy exercise. And now I'm going to make an observation. Check it out. All of this stuff here, we have a sum of a bunch of terms. Each term is a product of two factors that kind of always follow a pattern of sorts. A sum of products of two factors. Oh my gosh, that sounds like a dot product. In fact, one of these sets of factors are in fact exactly the coordinates of a very natural vector, right? X minus a. It's a very natural vector. A is the point where we're doing the linear approximation. X is the point where I'm evaluating that linear approximation. Hey, this makes great sense. This is a super reasonably natural thing. So, oh my gosh, it looks like it would make loads and loads of sense to view this expression up here as being a dot product, right? Structurally, it looks like a dot product. The blue stuff is literally a vector, right? So, in order to make this a dot product, I just have to kind of take all these green factors, define them to be the coordinates of a vector. This is a new vector that we haven't written down before. I'm going to call this thing the gradient. We're going to use this notation. It's a pretty standard notation. This is sort of an upside down triangle. Do make sure that it points upside down. The pointy end has to be down. If the pointy end goes up, that means something very, very different that we will also talk about later in this course. So pointy end down. Sure enough, this vector is a way to rewrite sort of the factors on the left there, and in so doing, notice that all of that stuff in purple conveniently and compactly rewritten as a dot product. Is that cool? Everybody with me? All right. Now, some of y'all may have heard of the gradient previously. There's a lot to say about gradients, and we'll do some of that today, but most of that down the road a bit. For now, this is largely just a notational convenience. It just it allows me to take a lot of stuff, including a yada yada yada, right? Dot 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 here. I'm sweeping a bunch of stuff under the rug. That's unseemly, right? And I can make that much more compact and crisp just by rewriting as a dot product. That's all we know about the gradient so far. Yes.
So is a gradient like it's a vector of like just functions?
It's a gradient. It's a vector whose coordinates are partial derivatives. And if you're talking about in general, then yes, it's a vector of functions. But we're not really doing that. You'll notice what we're interested in here is you can see right here, functions that are evaluated at a point, right? So all of these are evaluated at the point A. So since we're only looking at the point A, this is actually a vector with whose coefficients are just numbers. Yeah. Totally. Yeah. Okay. Anybody else? Okay. Excuse me. Okay. Alrighty. While we're here, I do want to take a quick moment to recognize that our old linear approximation formula up there and our new linear approximation formula, my gosh, the form, right? Very similar. F of A plus, and then in both cases, it's something times X minus A. Sure, X minus A is a vector down here. It was a scalar up here. Sure, it's a dot product instead of a scalar product. Okay, yeah, fine. But still, you got to give it to me. Those are pretty analogous. And the nice punchline then is that suggests that the gradient, maybe I should think of that as being pretty analogous to a derivative. It's playing a role here in linear approximations that is just like the role that the derivative played in single variable calculus. And so you may recall, when we first started chapter 2, when we first started section 2.3, I made this claim that there's going to be several different kinds of derivatives we're going to talk about in this class. This is one of them, right? This is one of them. We already did partial derivatives, but now here we have a different thing. The gradient vector. It's a vector, not a scalar, but in its way, it plays a role kind of like a derivative. And by the way, it plays other roles kind of like derivatives that we're going to see in a few. Okay. Alrighty. Let's see an example. Now this is very plug and chug, so I'm just going to point very quickly through this. Here again is our formula for a linear approximation. that I'm just going to straight up plug into. We're going to write down the linear approximation for a particular function at a particular point. And you'll notice that for a given function at a given point, I can literally just plug that point into that function, and not hard to see that that ends up being 5 arithmetic. Okay. Plug and chug, nothing happened. Now a little bit more to do here to talk about the gradient. The gradient consists of all the partials, and I do have to therefore compute various partials. Make sure you can do that, right? That's something you need to be glass smooth at computing, right? And don't forget, so easy to mess these up. So easy as you're taking a partial with respect to one variable and then a different variable to forget which role, which variables are playing. When you're taking a partial derivative, in this case, one of the variables is a constant. The other variable is not a constant, and then it switches when you do the other one. It's easy to mess that up, right? So have a system to make sure you're really, really reliable at that. And then let's see, again, I need to plug in the point A, right? And then all together, this factor in our dot product is that right there. Is that cool? Is everybody happy? Let's just plug and chug. Right. Okay. Do that. Okay, let's see. Lastly, don't forget that the point A right there is 1, 2 that was given. Don't forget that the vector x, and again, there's different notations I'll use at different times. Very often in the way I'm doing things these days, I would call this R. I'm not sure why I wrote this as x here, but it doesn't matter. It's just a notation. Point being, this is the vector x comma y, and so that goes there, and bam, we're done. Right? There is your linear approximation. And if you want to multiply this out, you can execute that dot product and collect terms, blah blah blah, and you'll end up with this, and that's fine too. There's a question as to whether you should do that or whether you need to do that. I'm going to say it depends on the circumstance, right? If the question just says find the linear approximation in a class like this being a math class, honestly, I would just leave it in the purple form here. Because there's information visible in how this is written. You can see the value of the function. Let me do that in a different color. The value of the function. You can see the gradient. You can see the point where you're doing the approximation. It's really nice. All of that's hidden if you multiply it out and collect terms. On the other hand, if the question says to multiply it out and collect terms, then do so. And if you're taking a class, or if you're in some sort of applied circumstance, maybe while y'all are working as engineers or what have you, and you're going to be coding this into a program that's going to run 1 billion times or whatever, you want to streamline things, make things as fast as possible. Oh yeah, multiply it out. Absolutely. You got to, everything's got to be as efficient as possible. Then yeah, of course, multiply it out. But I emphasize that's not what we're going to be doing in this class. Okay. How are we doing on this example? Is everybody? Yeah. Okay. Reminder. We've generalized from one variable to several variables. But we kept it real valued, just like the single variable case was. So now we have a natural next question. Okay, now we know how to do this if there's several input variables. Natural next question. What if there are also several output variables? And here's the answer. The answer is it's got the same form pretty much as we just saw. Rather than write out all the terms and then and then sort of collect them in with a convenient notation. There's too many terms. It would just be too ugly. I don't think that makes any sense. So I went straight to the sort of compactified version, and now I got to tell you what this df is. This df is this matrix right here. This is the thing that does it. We're going to check that. I say y'all are going to check that. Again, just a suggested exercise, but y'all can confirm for yourselves, and I think everyone should, and it shouldn't take you more than a few minutes. Maybe do this for like 2 or 3 input variables, 2 or 3 output variables. Don't go crazy, right? And just write that down. Expand this all out. Make sure to identify, wait a minute, what's a constant and what's a variable. And with all of that written down, you can then explicitly confirm that that function agrees with f in value, and that function agrees with f for all of the partial derivatives with respect to all of the different input variables of all of the different output variables at the point A. So yeah, again, maybe pick n equals 2, m equals 3, or something like that, and then just explicitly crank it out and confirm. And it's just algebra, and anyway, I think it's very doable and worth your time. Okay, now a couple things I need to say about the matrix. I'm sure you've noticed everything in here is a partial derivative. So it's a matrix where you just take all the partial derivatives, all the inputs, all the outputs, just all the partials, and just kind of toss them on in there. The asterisk is they have to be put in the right spot. This is all very delicate. You cannot sort of just organize them however you feel like, right? So in particular, notice that the columns correspond to input variables in the sense that in this first column, all the partials are with respect to the first input variable. So first column, first input variable. Second column, second input variable, et cetera, and then you'll notice last column are all partials with respect to the last input variable. Okay. Then you'll also notice all of the rows, they're partials with respect to a bunch of different input variables, but they're all partials of the same output variable. The same component function. Okay. So that's the pattern. Columns correspond to input variables, rows correspond to output variables, and if you keep everything in order according to those 2 rules, then you'll have it right. Okay, and by the way, it is so easy, and I see this regularly on exams. It's so easy for students to kind of get these 2 things switched and accidentally transpose the matrix, and it's a real problem, right? That's the kind of thing that'll make your bridge fall down, right? It's wrong answers, right? And importantly wrong, and so you've got to get this straight. So be extra careful about that. Okay. Let's see an example, and again, it's pretty plug and chug, so I'll be quick about it again, but here's our formula for a linear approximation. We're just going to plug into it, and notice our function at that point. Well, you can just plug that into there, and color coding. This becomes that. Just plug and chug, right? Nothing to it. Everybody happy with that? A little bit of an eyebrow raiser. A lot of students are a little confused the first time they write this down. They're like, "Whoa, hey, I got a vector here. What's going on? Why do I get a vector?" Well, right, because this is a vector-valued function. All the values of this function are vector. They're 3-dimensional vectors because this function has 3 components. So they better be vectors. Right? Everybody happy? Okay. And then again, you got to compute the df matrix. That's all the partial derivatives. Again, you have to evaluate that at the point A, so you plug those values into that derivative matrix, and therefore the actual vector then, the actual matrix is this right there. Yeah.
How come for the middle row of the matrix you didn't take the derivative like you did the other two equations?
I think I did. Did I mess it up? So let's think this through. Let's be careful.
Oh,
you start.
Yeah, one time. So I see.
Okay.
I see. Thank you.
Okay. Yeah. No. So great example. And I'm not picking on you, not at all, right? But it is so easy to wait a minute. Which variable is playing what role, right? So please be very, very careful. You don't want to whoopsie that kind of thing on a test. I flub that. Every so often, I have to keep myself honest. I have to, I don't blow through and do it as fast as I can. I have to pause periodically and say, okay, did I do my job? Am I, in this first column, am I treating y as a constant in all of this? I have to triple check that. Okay, all right. Okay, moving along. We've already made this observation kind of, but I'll do it again. The columns correspond to an input variable, and so therefore each column is a partial derivative of the vector valued function. And we've also made the observation that in each row, we're always taking the partials of the same component function. And we already know that the various partials of a given single function is called a gradient. So all the rows are gradients, sort of component gradients, and all the columns are partial derivatives. So that's kind of a neat fact. This observation here is mostly just a terminology. I'm not sure if y'all noticed, but if you look at this formula right here, that is not a linear transformation. Linear transformation sends 0 to 0. This doesn't. This sends 0 to f of a. It sends 0 to, some weird expression, or whatever that is. Right? So, not a linear transformation. So why do we call it a linear approximation if it's not linear? And there's a valid gripe there. Different ways you view this. I will note that sometimes the word linear is used in a different way. Right? The word linear sometimes means that it's kind of like a line, which in some contexts just means that things are kind of flat in some sense. Right? And that's just a different usage than the word linear, meaning linear transformation. But I will point out that the derivative matrix, which does all the heavy lifting of the linear approximation, being a matrix, it is literally a linear transformation. And so a case could be made because most of what we're doing with L is what this does, and that is linear. Maybe there's a case there. Anyway. Don't worry about this term affine. It's basically just it's a word that we put on this situation to fix it. But you don't need to worry about that. Okay, flashback again. So tangent planes. I'm sure y'all remember tangent planes. And let's see here. The problem I want to point to is that tangent planes are very often in Calc 1 classes conflated with linear approximations. And again, that's not right. Right? A linear approximation is a function. A tangent line is not a function. A tangent line is a curve, right? It's a geometric object. It's just not the same kind of critter. Now they're related. The linear approximation, which is a function, its graph, when you set its output values equal to a new variable, in this case y, its graph is the tangent line. Right? But we can't conflate the function and the graph of the function, right? So these two things are different. The tangent line and the linear approximation, just that, seemingly subtle difference, but in terms of the kinds of objects they are, well, they're completely different. Okay, with this in mind, we're going to make the same distinction, thinking about linear approximations of functions of two variables. Here's our formula. That's the linear approximation. The different thing that we want to relate it to is the graph of that linear approximation. And when you write this down, z equals, and then you look at the formula for the linear approximation, what you're going to get is a plane. And then let me further note, this plane that you get, well, the linear approximation agrees with f in terms of value, so they both go through this point. And the linear approximation agrees with f in terms of partial derivatives. So this plane and the graph of f itself are going to have the same sort of cross-sectional slopes. And so, reasonable to call this the tangent plane. Everybody buy it? All right, so hopefully no surprises there. Again, the big point is let's not conflate a function and its graph and case in point. So this is really just a rewind to something we already talked about. By the way, now real quick pause. Is it just me or is it really warm in here?
Yeah.
Okay, I thought so too. I wonder if somebody messed with the thermostat. I'm just going to look really quick. I'm up here sweating. And let's see here. Yeah, somebody had it set on 85. I didn't do it. Okay, got it back down. Oh, okay. It'll cool off now any second. Now, by the way, if at any point, if y'all get physically uncomfortable, feel free to shoot up a hand, okay? Because if you're warm, I'm almost certainly warm as well. So don't be shy about that. Okay. Moving along. Okay, so going back to where we first wrote down linear approximations, and I say if it exists, right? And you gotta say this because you can't just go writing down formulas if the function might not even have a derivative. You can't talk about f prime if f isn't differentiable. You just can't. Right? So in the single variable case, when does this exist? Well, the function has to be differentiable. And by the way, let's talk about what differentiability means. In Calc 1, it's not much of a concept, really. Differentiable just means you can take a derivative. It's grammar, really, more than anything else, right? It's not a subtle, sophisticated concept. Okay. It's much more sophisticated and subtle and weird in a multivariable setting. If I had an extra week of class time to spend on the subject, I could tell you everything that you could reasonably want to know about multivariable differentiability. It's subtle, it's weird, it's counterintuitive, there's some spooky, strange stuff out there. It is way more complicated than single variable differentiability. It is not just as simple as, well, you can take derivatives. It's just not. So I want to show you some of those weird things, just so you know what to be afraid of. And we're not going to go through these 2 pages. You can see it says optional. You don't have to look at this stuff. I will point out that it does culminate in what I'm going to call the definition of differentiability. Is that this complicated looking expression right here has to have a limit of 0 as you approach to point A. And there's a lot of discussion as to why is this a good definition. And again, we just don't have the time. And again, it's mathematicians enjoying the rigors of math more so than, it's not something that engineers would probably find super useful. But I want to show you some weird stuff. So this is on Desmos that y'all are probably already familiar with. And so I've entered in a function here. You can see it's not a particularly weird function. By the way, we're looking at the graph of that function. You can see it says c equals. Okay. And r sine 3 theta. That's it. That's the whole thing. Not scary looking. R sine 3 theta. Innocent looking little function. Right? I claim this is a severely screwed up function. Severely. And you'll kind of get the image as I kind of rotate it around. You can see it's pretty smooth looking, like sort of along and on these lobes kind of hanging. Oh, look at that. It'll rotate. I didn't know it would do that. That's awesome. So it's kind of smooth looking sort of over here and everything. But look what's happening at the origin. Can y'all see there's this weird kind of, I'd call it a corner, but it's weirder than a corner. You know what I mean? But very strange something is happening at the origin. Right? Here's one of the really strange things about it. I took a screenshot so that I could draw on it. One of the really strange things about it is if you look at that origin and then you look at the various cross sections going through that origin, straight line, I mean straight, perfectly straight line there. If you were taking a partial derivative in whatever direction that is, partial derivative, no problem, all good. Right there. Straight line. No problem. Right? And then likewise in that direction is straight line. In some sense you see how there's various kind of hills and then various kind of valleys on the opposite sides. And if you were on skis and you were at the top of one of these hills and just go straight down, and you probably ought to jump as you go over the origin, though you hit the sides, right? But anyway, it goes right on down the center of the valley down there, right? But in other directions, it's going upward. Let's see if I can. Well, let's see how do I want to do this. Maybe that's enough. I think the picture will just get more contorted. But if you look at the partial derivatives of this function at the origin, you would never notice anything wrong with it. All the partial derivatives exist. In fact, we're going to eventually see something called a directional derivative, which just means kind of like a partial derivative, but in a different direction. You can do directional derivatives kind of whatever direction you want. Not only do all the partial derivatives exist, all the directional derivatives exist too. This function is fine in terms of all directional derivatives. And yet, we're back to look how ugly this corner is at the origin. Something's gone terribly wrong. Partial derivatives are not up to the task of noticing what is terribly wrong with this function. Neither are directional derivatives. Everybody see what I'm talking about? So if we're going to talk about tangent planes, right, I hope we can agree there is no reasonable tangent plane. Nothing I could claim reasonably as a tangent plane to this function. If we're going to talk about tangent planes, it is not good enough to just say that the partial derivatives all exist. That worked in single variable. It doesn't work in multivariable. Even talking about all directional derivatives existing, not good enough. It just doesn't do the job. So this is just one example of something that we have to be really, really worried about. And that's why multivariable differentiability is an ugly matter. And we've got to write down ugly ugly expressions to deal with it. Okay. All right. So that's why we care. Oh, let me say another thing about it. So if it's so ugly, why do we care about this at all? How about we just skip the whole thing? Why worry about differentiability? And the answer, there's a really good answer. Differentiability is exactly the strict condition that makes certain very, very important theorems work. And remember, if you're going to write down a theorem, you have to have conditions. You have to know when it works. You want those conditions to be strong enough that they actually make the theorem work. But you don't want them to be too strong so that the theorem doesn't apply to functions that it should apply to. There's that perfect balance of exactly what we call the strict condition that would make it work. And the answer is differentiability. This ugliness is what we have to have. So it's really annoying. Here's the good news. Back to how are y'all as mostly engineers going to deal with this? And in the great majority of cases that you're ever going to experience, this is what you're going to do. You're going to talk instead about this very closely related idea called continuous differentiability. It's oddly convenient. It's super easy to work with. If you want to know if a function's continuously differentiable, just take the partials, world's easiest derivatives, check that they exist. Right? Well, I mean, come on, no big deal. Make sure nothing blows up. And then make sure that they're continuous. And let me just remind y'all, this is kind of a callback to Calc 1, but there's a huge category of functions that are all continuous where they are defined. Polynomials, exponentials, logs, trig functions, sums, differences, products, quotients, compositions of all of these things in any order, in any way, are all continuous where they are defined. And you might be thinking, whoa, now the tangent's not continuous, right? Tangent has a nasty discontinuity. Yeah, where it's not defined. Right? Tangent of pi over 2 is not defined. Everybody see what I'm talking about? Right? So, practically any function you can write down. There are some functions that are designed in some sense to circumvent this obstacle. Have y'all seen the Heaviside function? Okay, some of you have seen the Heaviside. Don't worry if you haven't seen it. It's not a big deal. The Heaviside function is, in some sense, designed to be a counterexample to this claim. Anyway, but anything that, again, polynomials, exponentials, logs, trig, oh my gosh, anything that you would normally routinely write down, continuous where it's defined. So it's really easy to check. And so, for example, if I want to know I'm sorry, and then I got ahead of myself. Once you've checked continuous differentiability, it immediately follows the function is differentiable. This thing that would have been a nightmare monster to deal with otherwise, if you just check continuous differentiability, so easy, that allows you to conclude the differentiability that you want. In practice, day in and day out, that's how you do it. And I think this example is a pretty straight read here, but let's take a quick moment to talk through it. How do I know this function's differentiable? Well, I'm going to compute the partials. They're all polynomials. Polynomials are all continuous, right? As per we just discussed. If the partials are all continuous, that's what continuous differentiability means. And if we have continuous differentiability, then it follows that the function is differentiable. So, boom, boom, boom. Everybody happy? Okay. A couple of little quickie things. This counterexample is, you can take a look if you like. It's not a big deal. But neat fact, differentiability implies continuity. I hope that's familiar. You probably remember something along those lines from Calc 1. The contrapositive is where it gets kind of useful. It becomes a differentiability test. If a function fails to be continuous, then you don't even need to ask the differentiability question. It's definitely not differentiable. Again, this is called the contrapositive of this original statement. Okay. Let's see. Here's my glasses. All right, I'm going to go ahead and give up on the last 5 seconds. So y'all have a good rest of your Monday. See you later. I'll draw the line right there. Okay. See you Wednesday.